Hello students, today we are trying to solve another problem, previously problem from KTU. This was asked in 2017, July in MOS. So this is from the module 5, stress transformation portion. Okay, so we'll read out the question. We'll try to understand the question first. At a point in a material, stress components are Px, Py and Q. So Px is 500, Py is 100 and Q is 20. Determine 1. The planes on which shear stress is maximum, principal planes and stress components on these planes. Okay, so Px, Py, it is not the normal representation. Sigma is what we use. Px, Py is normal stresses. Q is a shear stress. So if I draw a stress block, it should look like this, something like this. So let me. So if I assume this direction as x direction, this is y. So the value in x direction, the stress in x direction is given by 500 MPa as 500 MPa. Y direction is given as 10 MPa. And shear stress, the sign convention is not given, so it is plus 20 MPa. So let's assume it will be plus. So it will be something like this. So once I draw a shear stress in this side, I have to automatically draw a shear stress in this side for vertical equilibrium. Then it will have a rotation instability. It will try to rotate in anti-clockwise direction. To prevent that, we need the complementary shear stresses. Okay, the value of all the shear stresses is nothing but 20 MPa. 20 MPa. Right. Now, the question they asked is first the planes in which shear stress is maximum, principal planes. So first, what we'll do, we'll try to solve the principal plane part. Principal planes. Okay. So what is given to us is sigma x. The value of sigma x is 500. Sigma y is 10, and tau xy is 20. Okay. Now for principal planes, we know that we can use the formula tan 2 theta p will be equal to tau xy upon sigma x minus sigma y by 2 is equal to 20 upon 500 minus 10 upon 2. Okay, so this is nothing but 20 upon, so this is 490 by 2, which is 245. So 2 theta p is tan inverse of 20 upon 245, which comes out to be 4.666 degree. So principal plane is equal to 4.666 divided by 2, which is equal to 2.33 degree. So this is one principal angle. Second principal angle we can find by adding 90 degrees to this, equal to 2.33 plus 90, equal to 92.33. Okay, so these are two principal planes. Now we can attack the second part of the problem, that is, sorry, the first part of the problem, which is plane of maximum shear stress. Okay, plane of maximum shear stress. So maximum shear stress, plane of maximum shear stress. So I'll call this plane as theta s. We know that the relation between theta s and theta p is theta s is theta p plus minus 45 degree. Okay, so this will be equal to 2.33 plus 45, which is 47.22. Also we can find second values, or theta s is 2.22 minus 45, which is equal to so it is 2.33. So before mistake. Three, 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 three. Is equal to 42.6. So negative theta means it is we have to rotate the block in clockwise direction. Positive theta means we have to rotate the block in positive direction. Okay, that is counterclockwise direction. So this answers the first part of the problem. So we have found that also. Then they are asking what is the stress components in these planes. Okay, so they are asking what is the stress components in principal planes, what is the stress components in plane of maximum shear stress. Okay, so that also we have to answer. So let's see how to answer that. So first what we'll do, we will try to find the stresses in principal planes. Okay, so principal plane stresses are given directly by the equation. Stresses on principal plane. So we know the equation sigma 1 to sigma 1 comma 2 is given by sigma x plus sigma y by 2 plus minus under root sigma x minus sigma y by 2 whole square plus tau x by whole square. Okay, sometimes this portion is what is also called as average stress. This portion is nothing but the radius of the Mohs circle. Okay, so we can find these two parts separately. So sigma average is 500 plus 10 by 2, which is equal to 255 MPa. 255 MPa. R equal to under root of 500 minus 10 by 2 whole square plus 20 square, which comes out to be 240 245.8 MPa. Okay, so I have sigma 1 and sigma 2 here. Sigma 1 equal to this plus this 255 plus 245.8, which is equal to 255 plus 245.8, which is equal to 500.8. So approximately 500 MPa, 500.8. Okay, and sigma 2 equal to 255 minus 245 245.8. So that is 9.2. Sorry, 9.2 MPa. We can always check sigma 1 plus sigma 2 equal to 510, which should be equal to sigma x plus sigma y, which is also equal to 510. So this always should be true. Okay, any angle, any planes stresses in normal stresses in any plane, if you add them, it should be equal to the normal stresses in any other plane. Okay, so this you can always check. This is a check. This is check. It is not required, but if you do this, you can be more confident of your answer. Now I will just draw this also stress block. So this is my original stress block. So this again, it is for your understanding that I am doing this. So this is stress block, original stress block. So I have to rotate by some very small angle, 4 degree. Okay, rotate by 4 degree, sorry, 2.33 degree. So this angle of rotation is 2.33 degree. So this will give me principal plane. So principal plane means there will be no shear stress in those planes. So this angle of rotation is nothing but 2.33 degree. Okay, so if you answer it with this graph, it will be better. So one direction it is to 500.8, other direction it is 9.2, and shear stress is 0. So this is the orientation of principal plane. So this is one principal plane, this is second principal plane, this is third principal plane, this is fourth principal plane. So this has angle 2.33, this has 2.33 plus 90, this has 2.33 minus 90, and this is 2.33 plus 190. So those are the different angles of the planes. Okay, so these four principal planes will get. These stresses are equal and opposite. So generally we consider only these two, because this and this are parallel planes, this and this are parallel planes. We can assume these two planes will be having same angle. So this one angle and this one angle we will say. Okay, this is 2.33 plus 90. We can say, once you say this, this is also included because these two are parallel. Once you say this, this is also included, right? So this is first part. Now if you draw this, it is bonus. It will show that you have the correct understanding of the subject. Now we have to find stresses in this plane, okay, where the shear stress is maximum. So this also we can answer. For this we have to use the formula of stress transformation. Okay, so in this sigma x is again 500, sigma y is 10, tau xy is 20, and theta that we have to consider is 47.33. So this gives me 2 theta equal to will be equal to 94.66. Okay, so this is one angle that we can consider. So let's see what we are going to get. So stress transformation equations, this you have to remember this equation. Sigma x dash equal to, so sigma x dash is the stress in theta direction. Okay, sigma x dash is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos to theta plus tau xy sin to theta. Sigma y dash, which will be equal to sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 cos to theta plus tau xy sin to theta, and shear will be equal to minus of sigma x minus sigma y by 2 sin to theta plus tau xy cos to theta. So these three equations you have to remember. Now if I substitute these values, sigma x, sigma y, tau xy, what you get is 255 MPa. So I am not doing that. If I substitute these values, what I'll get is again I'll get something around 255 MPa. So this is approximate values. Okay, you can calculate this, and when I substitute this, what I will get is 245 minus 245.81 MPa. Okay. Now if I want to draw the stress block, so that also can be drawn. So very quickly I will draw that. So this is the original stress block. From this stress block, I have to rotate have to rotate this by 47.33 degree. Okay, so this I'm just approximately I'm rotating 47.33 degree. Okay, this is 47.33 degree. So let's say this is 47.33 degree. So what I have is stresses. This is sigma x dash, this is sigma y dash. So this stress is 255 MPa. This is also 255 MPa. And the shear stresses, so it is showing negative, so we have to show like this. Is equal to 245.81. Okay, so this is a solution to this. So this orientation, it is not required to draw this, but if you can draw this, well and good. Okay, so I hope this is clear. This is how you solve this kind of problems. So it's for 14 marks asked in 2017. So again, students should be very careful about these two formulas when to apply these two formulas. When you want to find stresses at a particular any given angle, you have to use this formula. If you want to find the principal stresses, you have to use this formula. So we will see in another video with another problem. Thank you.